Hi guys, welcome back to a new IMONST video. So in this video, we'll be talking about problems 14 to 17 for junior, sample 3 paper. And for seniors, it'll be questions 9 to 12. So let's look at problem 14. Determine the largest multiple of 125 with all its digits different. So when doing this problem, we need to consider two main principles. So the first principle would be more digits, better. So since we have all its digits different, it means that we are allowed to use all the digits from 0 to 9 exactly once, because all its digits different, use 0, 0, it's not possible, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, all of these you can use once. And then the second thing to consider is that we would want our front digits. So maybe say if you have a 5-digit number, you want your tens, thousands digits to be the maximum, to be as big as possible. Front digits as big as possible. Let me demonstrate by using an example. So I give you 4, 6, 7, 9. Of course, how would you want to form the biggest number? Of course, you want to use up all 4 of these digits, right? And then for the biggest one, so this thousands has the most impact. So between, say, if you want to put 7 or put 9 here, of course you want it to be bigger, so 9. And then the next biggest one, you put it the hundredth digit, 7, and then 6, and then 4. Now, since this is a multiple of 1 to 5, we need to also consider a thing that the multiples of 1 to 5, so last 3 digits of multiples, I'll just use a contraction, multiples of 1 to 5 are repetitive, are repeating. Why is this so? Let me show you in a second. Now, let's start the first few multiples of 1 to 5. This is a very easy task. You just add 1 to 5. So 1 to 5, 250, 375, 500, 625, 750, 875, 1000, and then you see 1000, you plus another 1 to 5, you would get 1125, right? So this 1125, the last 3 digits is the same as 1125 over here. So the next one 1250, same here, and then this thing will repeat. So it will repeat once every 8 terms, right? So we want to see okay, using the second principle, since our front digits should be as big as possible, we want our digits at the back, since 125, 250, all of these are digits at the back, to be as small as possible. So we need to consider 2 things. So 1, the digits cannot be repeating. 2, the sum of the digits must be as small as possible. So let's look at these, which fits to the 2 of these criteria, okay? So 1 plus 2 plus 5, as we can see here, would be 8. Then this one, 2 plus 5 plus 0, 7. 3 plus 7 plus 5, 15. 5 plus 0 plus 0, since we have 2 zeros here, we cannot use this. This is out. 6 plus 2 plus 5 is 13. And then 7 plus 5 plus 0 is 12. 8 plus 7 plus 5 is 20. And then you see another 3 zeros, so no. So out of these, the smallest one is 250, which is a 7. So we know that this multiple of 125's last 3 digits is 250. Then using the second principle, the front digits should be as big as possible. Just put up 9, 8, 7, 6, 5. We used that already, right? So 4, 3, 2, no, 1, 250. So our final answer for problem 14 is just 9876, 431, 250. Okay, so this is a very quick, because last time I recorded it, this is it took like 7 minutes to explain this problem, which is a very I don't know. Okay, now let's look at problem 15. Given a sequence of integers a1, a2, a3 starting from the third term, each term is equal to the sum of all previous terms. So, okay, it is known that a1 equals 1 and n is the largest possible integer with an equals to 10,000. Find a2. Now, since we are starting from the third term, so the third term will rely on the first and second term. We know our a1 equals to 1, and then we can set our a equal to be some x, okay? No, we just put it as a2, okay? So our third term, a3, would be a1 plus a2. Then our a4 would be a1 plus a2, and then plus the a3, which is itself also a1 plus a2, is 2a1 plus a2, okay? And then a5 would be a1 plus a2, and then plus this a1 plus a2 again, and then plus a4, which is 2a1 plus a2, is 4a1 plus a2. Okay, now I'll just use 2 apostrophes to represent a1 plus a2. Okay, so a6 is a1 plus a2 plus a3, which is a1 plus a2, then plus a4, which is 2a1 plus a2, and then plus a5, which is 4a1 plus a2. So 1 of these, 2 of these, 4 of these, 8 of these. So a6 is 8a1 plus a2. Right. As you can see from the third term, it's always in terms of a1 plus a2. It's just a matter of how many of these, right? So for a3, we have 1 of them, and then a4, we've double it. Then a5, we double the previous term, a6 double of previous term. So since we're just multiplying stuff by 2, we could generalize this to become something like, for an, it would become 2 to the power of I don't know what, and then it will be in the form of a1 plus a2. So we can see, okay, so a4, a3, we have 2 to the power of 0. a4, we have 2 to the power of 1 of these. a5 is 2 to the power of 2 of these. And then a6 is 2 to the power of 3 of this a1 plus a2 thing. So you can see 6 minus 3, 5 minus 2, 4 minus 1 all have a difference of 3. So we would have an equals to 2 to the power of n minus 3 times a1 plus a2. So what we want to do is we want to see how many 2's are hiding inside this how many 2's are hiding inside this 10,000, so that we can maximize our 2's, right? Okay, so we know that 10,000 is 10 to the power of 4, which is 2 times 5 to the power of 4. So let me move down a little bit. Oh, we have shown you problem 16. Okay, it's okay. So move down a bit. So from the question, 10 to the power of 4 is 2 to the power of 4 times 5 to the power of 4, right? So 2 to the power of 4. So an would be 2 to the power of n minus 3 times a1 plus a2. Now, since we want our n to be a maximum, right, as shown in the question, where's the question? That's okay. We want n is the largest possible integer with a n equals to 10,000. So since we know that 10 to the power of 4 can be divided into at most 2 to the power of 4, so our n minus 3 max is 4, and then our n max is 7, right? So a7 is equals to 2 to the power of 4. We know that a1 equals to 1, and then a2 is just what we need to find. And we also know that this a7 is actually 10,000 as shown in the question. So our a2, so we know our 1 plus a2 is just 10,000 divided by 2 to the power of 4, 16. It will give us 625. Then minus both sides by 1, we will get a2 equals to 624. So this is our answer, okay? Just note that our n must be the maximum and stuff, okay? So we're done with problem 15. Now, let's go to problem 16. This will be a long one because the last time I recorded, this is a re-recording, and then the last time I recorded, it took like 12-13 minutes. I want to try shortening it, okay? I apologize for that. Now, how many palindromic integers are there that remains a palindromic integer number after addition with 2020? Then, as you can see, they gave us the definition of the palindromic integer. If read forward or backward, it remains the same. So these are examples. Now, we need to divide this into several cases, and then we want to see if there are any numbers that, if there are any numbers in that case that satisfy the condition. Now, so I will be using p dot I dot as to represent palindromic integer. Okay, so we need to divide this into several cases. So case 1, the palindromic integer has 1 digit. So it's just any single digit number from 1 to 10, okay? So 2020. It could be represented as a. And then this line above a just means that this a is a digit. It's not a number, okay? So 2020 plus some a would be 202a. So since we want it to be the same read forward or backward, so a must be equal to 2. But we see 2022 is not the same read forward or back. So 2202. How are they the same? So none of these work. So for case 1, which is a 1 digit, we would say this is not applicable. So none of these can fulfill the conditions, right? So we will want to see the second case, which is the palindromic integer has 2 digits. So it will be represented in the form of AA. So same if read front or back, right? So 2020 plus AA would be 2, 0, this one 2 plus A, and then we have A. So if you want this to be read the same as from front and to back, A must be 2. And then 2020 plus 22. So 2020 plus 22 would be 2042. And then if we read this from back to front, it's not the same. So again, case 2, so 2 digits, would be not applicable also. Okay? So none of these will work. Now, for the third case would be our palindromic integer has 3 digits. So for 3-digit palindromic integer, it will be represented in the form of A, B, A. Again, the line above it just represents that A, B, and A are digits, so not some number from 0 to 9. Okay, won't exceed 10. Okay, now 2020 plus A, B, A. We need to cap a minimum for this thing. Okay, so the maximum for this thing would be 2020 plus 999, because 999 is the largest 3-digit integer, would be 3019. So the thousands digit will either be 2 or 3. So our units digit should either be 2 or 3. Okay, so thousands digit, I'll just use D, will be either 2 or 3. So our units digit should also be something like 2 or 3. So if our thousands digit is 3, right? So then our units digit is 3, then 2020 plus 3 something 3, 23 something 3, which is not 3000 yet. So this one just fails directly. So for the case it's 3, there are no cases. And then for 2, so let's see, okay? So if our thousands digit is 2, the units digit is also 2, so 2020 plus 2 something B2. Okay, this will be 2222 plus 10b. So, okay, because b is in the tens digit, right? So what is the next palindromic integer after 2222? It will be 2332. But then this would be a 110 increase. So 10b, if 10b is equal to 110, b would have to be 11. But b cannot be 11 since b is a number from 0 to 9, right? So the case for 2 will only work if b equals to 0. Okay, so b equals to 0 case works. So there is indeed one case if the palindromic integer is a 3-digit. So for the third case, 3 digits, I'll just use D to represent digits. One case. Okay, now let's move on to case 4. Okay, so we are quite fast, and I hope you guys are not left out. If you do feel that something is not understandable as of now to you, you could just write it down in the comments. Now, for case 4, the palindromic integer has 4 digits. So we will have A, B, B, A, right? So 2020 plus A, B, B, A. Okay, something like this. Now let's cap a limit for this, okay? Maximum. We would have 2020 plus 9999 would be 12019. So it would give us either a 4-digit number or 5-digit number. Okay. But since our 5-digit number would be 1, it will have a 10,000th digit of 1. So we will have something like 2020 plus 1 something something 1. Which is 3 or 4, because if the middle one is 9, then it will be something 4 something. So this does not even exceed 10,000, so this is not possible, right? So we need to look at the 4 digit. Now 2020 plus ABBA, we would have so our A is at most 7, it cannot be 8, because until then it will become a 5-digit number. So we'll have 2 plus A, and then B, and then 2 plus B, and then A. is this the same read forward and backward? No, because you see the 1000th digit for the original number is 2 plus A, and then the 1000th digit for the number read from back to forward is A, so it's not the same. So there are no 4-digit numbers that can satisfy our case. So this whole case is basically a big fail. So no. And then now let's go back to our tally. So for the fourth case, for case 4, so this is 4-digit. This is also not applicable. Now we have at most 6 cases, to be honest. Now for the 5th case, where our palindromic integer has 5 digits. Okay, so let me write over here. Palindromic integer has 5 digits. So it will be represented in the form A, B, C, B, A. Now 20, 20 plus A, B, C, B, A. Now theoretically, we will have something like A, B plus 2, C, B plus 2, then A. Right. But now we have to be careful a little bit, because B plus 2 might exceed 10. Right. It might be larger than or equal to 10. So B would be larger than or equal to 8. Okay, so we need to consider 2 cases again. So let's do this. Now we will have to consider the cases where B equals to 8 or 9. Okay. Now, and then another case would be B would be from something from 0 to 7. Okay, so if B equals to 8 or 9, we would have 20, 20 plus A, B, C, B, A will give us, okay, since 2 plus B exceeds 10, so we have A plus 1, and then B plus 2 would be B plus 2 minus 10 would be B minus 8, and then C would be just C plus 1, because again this one B plus 2 exceeds 10, so this is B minus 8, and then this is A. Now read from front to back, this is not the same, so this cannot be a palindrome, so this case is cancelled. Now so for 0 larger than or equal 0 smaller than or equal to B, B smaller than or equal to 7, all of these cases work. So we just need to do a thing called permutation and combination. No, actually it should be read, I don't know how it's read, but permutation, combination. If you guys do not know what is this, you can search it up on the web to learn it, to solve this problem. I will not go into it deeply. Basically, because we just need to focus on A, we just need to see how many choices are there for our A's, B's, and C's, right? So our A could be any digit from 1 to 9, because A cannot be 0, otherwise it's not a 5-digit number. So A, we have 9 choices. Then B, as we said before, we have 0 to 7, because B is not the first digit. So B could be any number from 0 to 7. And then we will have 8 choices. And then C would be, because C again is not the first digit, we can let it be any digit from 0 to 9. We would have 10 choices. So 9 times 8 times 10 would give us 720. Now you might be asking, why would we do a multiplication? It's the same analogy as me asking you, how many 2-digit numbers are there? You say, oh, from 10 to 99, you say 90, but how does this come from? So again, so the 10th digit will be any number from 1 to 9. We have 9 choices, and then the units digit will be any number from 0 to 9. So 10 choices. So 1, 2, 1, 3. I like this. All of these combinations, 9 times 10 will give us 90. So this is how it came from. So for the palindromic integers that have 5 digits, there are 720 cases. Okay, so let me find my pen's position. It's a bit okay. 720 cases. Now, for 6-digit palindromic integers and above, we will be showing you in a minute that it is not solvable. So we do a case 6. Okay, so our palindromic integer has 6 digits. We could say or more. Okay. Now this would be represented in the form of A, B, C, C, B, A, right? So let's see. A, B, C, C, B, A plus 20, 20 would give us, okay, something like A, okay. Then maybe B, C plus 2, C, B plus 2, and A, okay? But if read from back to front, it will give us A, B plus 2, C, C plus 2, B, A. So as you can see, those are not the same. So this is cancel, and then this applies to all palindromic integers with more than 6 digits, say 7 digit, 8 digit. None of these will work. Okay, so in all in all, there are only 6 cases that we need to consider. So this is 6 case 6 is not applicable also. So we counted the tally. We have 1 case and then 720 cases. So in total, how many palindromic integers are there? So we just add up 720 plus 1, so we will have 721, and this in fact is the answer to problem 16. Now this is the last question of the day. So we have problem 17. Find the smallest integer n larger than or equal to 100 such that 2 to the power of n plus 2 to the power of 100 plus 2 to the power of 103 is an integer. Now we can say that 2 to the power of n, since n is larger than or equal to 100, minusing both sides by 100, we will have n minus 100 is larger than or equal to 0. So n minus 100 could be 0, 1, 2, 3, no one knows. And then, so we could say, let a equals to n minus 100, right? So, 2 to the power of n equals 2 to the power of a plus 100, because this is n minus 100. It will become 2 to the power of 100 times 2 to the power of a. Now, you can see that this one we also can take a 2 to the power of 100 out. We also can take a 2 to the power of 100 out from this, right? And then we also know that any number, a to the power of 2n, if we put it in the square root, it will give us a to the power of n. So, what we can do is, this thing, 2 to the power of n plus 2 to the power of 100 plus 2 to the power of 103 is equals to 2 to the power of 100. And then we 2 to the power of a, so this is 2 to the power of n, and then plus 2 to the power of 0, because indices add when we multiply, when the powers add when we multiply the kind of power, I don't know. Indices add up when we multiply the powers, and then 2 to the power of 3 over here. So this is 2 to the power of 103. We can take out the 2 to the power of 100. So we want to know that this is some a. If we square both sides, this one will become an a square. So if we take out this 2 to the power of 100, we will get 2 to the power of 50 times 2 to the power of a plus 1 plus 8. This thing is also a square number because this is also an integer, right? So 2 to the power of a plus 9 is some integer, let's say b. So 2 to the power of a plus 9 equals to b squared, and then since 9 is 3 squared itself, so 2a is equal to b plus 3, b minus 3. Okay, remember the a squared minus b squared formula? You go and check it yourself. Okay, so 2 to the power of a is equals to b squared, b plus 3, b minus 3. Since this one can only be factored into smaller powers of 2, meaning maybe say some 2 to the power of c times 2 to the power of d. So both of these are powers of 2. Then both of these differ by 6. And which powers of 2 differ by 6? So we only know that 2 to the power of 3 and 2 to the power of 1, which are 8 and 2 respectively, they differ by 6. No other pair of power of 2 differs by 6. You can check this for yourself. So we know that, okay, give me a moment. So we would have to write 2a is equals to 8 times 2 equals to 16 equals to 4. Now, since our a equals to 4, n would become 100 plus a is 104. So this is the answer to question 17. Now I hope, I know that I speak a little bit quickly this time, but I hope that you guys could understand my solution, and then I think the next time I'll just reduce the problem count in every time, okay? So that's it for today. I hope you guys had fun listening. I don't know. Okay, we'll see you guys in the next video. So ciao ciao.